probability of subcritical non-local spatial branching processes without and with immigration. Thanks a lot, Victor.
Thank you very much, Adrian, for the invitation and for the presentation. Can you see my slides? Is it okay? Yeah? Okay, good. It's a pleasure for me to be in this seminar, actually. I have seen it has been a very active seminar that I didn't know before, but I'm very happy to know it now, and I hope I can follow it from now on. Actually, hope we can join it from CIMAT more often. So as Adrian said, I'm going to speak about this work on stability of non-local branching processes with and without immigration. This is a work that I did while I was visiting the University of Warwick in collaboration with Andreas Cipriano, Emma Horton, Pedro Martin Chavez, and Ellen Powell. And actually, Andreas and Pedro, they continue working in this project together with Natalia Cardona. So there is another a continuation of this work on other conditions. Okay. Well, this is the agenda for the day. I'm going to give a brief introduction. I included some basic material on BNME Galton Watson processes with immigration to motivate the results we are trying to obtain on the long-time behavior for more general branching Markov processes. So later, after I describe these basic results that are actually well known and can be read for instance, in Tria Ney's book, I'm going to describe one of the main parts of the model we are studying, branching Markov processes, which are models where we allow movement and branching continuously. I'm going to describe a couple of examples, and then I'm going to describe the more general setting of with immigration, and then the setting of superprocesses. Okay, so let me just start with the introduction, the general ideas. We know that branching processes is just models that are used to describe the evolution of systems where elements like particles or cells generate new elements according to some rules. Okay, and I will be focusing on the asymptotic behavior of these branching models. In these models, we will be allowing reproduction, division, movement in a continuous matter. And we will be assuming that the particles are living in a complete separable metric space. And we will be differentiating between two cases when there are distinguishable particles. That will be the case of branching Markov processes, and where we cannot distinguish the particles, but rather we see some masses evolving. That's the case of superprocesses. Both will be in the case of with immigration. Okay. Usually, two properties are studied for this kind of models. Of course, there are many others, but it's studied extinction or explosion, and there is a kind of a duality. So I will be more focusing on models that have some extinction. Okay. And usually these models are classified in three large classes: supercritical, critical, and subcritical. So because I'm more interested on the extinction case, I will be speaking about critical and subcritical. Is everything okay in IMPA, or should I? Is it okay? Good, thank you. And more particularly, I'm gonna be considering results of the type Kolmogorov limit, Yaglom limit laws, and distributional stability. And well, I will describe the results in the more clear setting of branching Markov processes, branching Markov process with immigration, but these results are also valid in the case of superprocesses with or without immigration. Okay, so I go to the basic model. So in this part, we consider a BNME Galton Watson process with immigration. Okay, we will denote this process by Zn. Zn will be denoting the size of the population at the generation n, and this process follows the following dynamics. So the population at generation n plus 1 is made of the offspring of individuals from a generation n, okay, and a certain number of immigrants that arrive to the generation n plus 1, okay. All the immigration is independent of the previous immigrants or of the previous generations, okay, and they are all identically distributed. And it's important to say that they will be characterized by its generating function g, okay? And if we know that at time n, there are Zn individuals, those Zn individuals are gonna beget some a random number of individuals, Zi, for the I individual present in the nth generation, okay? And all the individuals are going to behave the same in an independent way. And the size of the typical families is going to be characterized by the generating function, a generating function f. Okay, and we will be assuming that we are not in the trivial case where there are either 0 or 1 descendants. Okay, so the probability of having 2 or more is strictly positive. Okay, so all the individuals are going to behave the same essentially and independently. Okay, so we have this sketch of the behavior. So we have an original individual. In the next generation is going to beget some individuals. In this case, it is 4, and they are going to arrive some immigrants. And once the immigrants arrive into the system, they are going to behave as the other individuals. Okay, so these individuals are going to beget a new population. Okay, and the other individuals are going to do the same. Okay, so in this case, this individual, for instance, doesn't have any descendant. This one has 3 descendants, and so on. Okay. Well, in the case we are going to be interested is the case where the population is critical or subcritical. In that case, the population may get extinct, is going to get extinct with probability 1 in a finite time. So there might be times where the population is 0, but because of the immigration, or where there is immigration, there are going to be some immigrants arriving later on that are going to recover the population. Those populations can still get extinct. So eventually the population is going to get extinct again. But again, there might be another immigrant coming and just behaving as the original individual in the population. And because of the independence, all these subpopulations are independent. So starting with said individuals is just summing the behavior of the said individual populations. Okay. Well, typically we study the size of the population using the generating function. So this is the generating function starting from said individuals. And at generation 1, we have the number of individuals that arrive and the number of individuals beget by the said original individuals. Okay, so if we iterate this expression and we see what happens after n generations, we are going to have the contribution of the said original individuals for n generations, and then this term that is going to describe the contribution from the individuals arriving at generation j that are going to contribute into the population for n minus j generations remaining. Okay, so that is giving this expression, and this fn is the usual composition of f with itself n times. Okay, this description we have here below is the same that I just said from the contribution of the descendants, of the immigrants in the previous generation. Okay, so this representation is actually very useful for studying the asymptotic behavior, because we can just take the limits and understand what is happening with these generating functions as n goes to infinity. So I can now describe what happens in when n goes to infinity. And there is a classical result by Foster and Williamson in 1971, where they prove that the size of the population at generation n is going to have a limit as n goes to infinity if and only if this integral criteria is satisfied, if and only if this integral is finite. Okay, and that is when the population is critical or subcritical. So when the size of the typical descendant, the typical family, is equal to 1 or smaller than 1. Okay, and then it's important to remember that without immigration, because we're in the subcritical or critical case, the typical population is gonna get extinct almost surely in a finite time. And this criteria is actually expressing a trade-off between the immigration and the extinction of the populations. Okay, so this is a term related to the immigration. This is a term related to the typical size of the populations, and we have to understand how this is behaving when s is close to 1, essentially. Okay, so coming back to the sketch I did before, well, these typical populations have some tendency to go to 0. These immigrants are going to recover the population, and the size of the population is going to stay in a control zone, or kind of controllable, if there are not too many individuals that are arriving too often, so that the population may go to plus infinity, and that cannot be controlled. Okay, that's a trade-off we are seeing in that integral test. I described it before. Okay, just to give an idea of the proof, as I said before, we have the generating function of the size of the population at time n that is given by this expression here. So we take the limit as n goes to infinity here, and the limit as n goes to infinity here, and we need to understand how this product is behaving, and we know that this product is going to have a limit if also the sum of the log of g of f k has a limit. And that series is going to have a limit if and only if this series is convergent. Okay, we just take log of 1 minus x. We know that it behaves like x. Okay, so to know the convergence of this product, we just need to study the convergence of this integral, and we can multiply and divide by some xk plus 1 minus xk, which is going to be a partition of the interval that is built by taking fn of s. That's going to give xn. And because fn plus 1 is f composed with fn, we are going to have that xn plus 1 is f of xn. Okay, so this difference here can also be expressed like f of xk minus xk. Okay, and then we can just approximate this series by an integral, because this looks like a Riemann series. Okay, so we study the convergence by studying this integral. Okay, well, that's essentially the proof of that key result. And actually, we can simplify that integral test, but by dividing into the cases where the population is subcritical or critical. When the population is subcritical, we have, that's equivalent to say that the mean of f, that the derivative of f at 1 is smaller than 1. And in that case, we can make a Taylor development of f around 1 of order 1, and express f of s minus s like 1 minus s plus the mean times s minus 1 times this error term. And that is can be just expressed like 1 minus m times 1 minus s times plus this little term. Okay, so this is just to say that this term is just like 1 minus s for s is for s very close to 1. So we can replace this term by 1 minus s, and this just becomes an integral test for the immigration, for the size of the typical immigration. Okay, that is what I said before, determined by the populations not being too large, the incoming individuals not being too large. So by doing that, we can just recover a classical result by Heathcote in 1966, where he studied the case of a subcritical population, where he proved that if the typical immigrant family has a log moment, a finite log moment, then set n is going to converge weakly as n goes to infinity. And if that log moment condition is not satisfied, then set n is going to go to infinity in probability. And well, it's also a good moment to recall another result by Seneta that I'm not gonna study the parallel later on, but well, that it is about the supercritical case. In the supercritical case, we know that if the log moment condition is satisfied, then set n grows exponentially fast with a rate that is determined by the average population size. Okay? And if the log moment condition is not satisfied, then we cannot normalize set n in this form. So there is no constant c such that this set n divided by cn has a limit. Okay, so it is necessary to normalize the population in a different way in the supercritical case, and there are studies about that. And our particular problem, I think it has not been studied yet, but it has to be studied. Okay, well, let me now describe what happens a little bit more in the critical regime. Okay, first, when there is no immigration, for the moment, I'm going to assume that there is no immigration. So it's just about the size of the typical families in the critical case. In that case, it is known that if the variance is finite, then the population is going to get extinct with probability 1, but it's going to take long time to get extinct. And actually, the probability of having an extinction at time bigger than n is going to decrease linearly with n. So we are going to have that n times the probability of having a population size that is strictly positive has a limit as s goes to infinity that's given by 2 divided by sigma square. Okay, and this estimate can also be used or can be made more precise to get a Yaglom limit that tells us that when n goes to infinity, set n divided by n conditionally on the population not being extinct at time n has that limit exists as n goes to infinity, and the limit is this exponential term. So this is just telling us that conditionally on the population not being extinct, set n divided by n converges in distribution to an exponential random variable of parameter sigma squared divided by 2. Okay. And when we have some immigration with a finite mean, so if the typical size of the immigrants has a finite mean, okay, and we have a finite variance for the typical size of the families, still we are going to have that set n divided by n converges in low, okay? But now the limit is not going to be an exponential, but it's going to be an exponential tilted essentially by the typical size of the immigrating families. Okay, so the parameter of the gamma random variable is going to be a parameter two times the mean of the typical size of immigrants divided by the variance of the size of the typical families. Okay, so here we don't need to condition the population not to get extinct. Okay, but the immigration has actually this is essentially the same effect when this mean is finite. Okay. Well, there are, of course, many other properties of these populations that can be studied, but I want to mention a particular one, which is about the times where the population get extinct, okay, the zero set for these BNMA Galton Watson processes. These sets have been studied by Clément Foucard and Jerónimo Uribe in 2014 in the continuous setting, in the setting of continuous time branching processes with immigration. There are previous studies in the discrete setting, but the results or their integral tests allow to study transients, zero recurrence of Zn, and positive recurrence. And that can also be used to study the excursions from zero for Zn or for the continuous time branching processes within migration. Okay, so this is about the basics of these BNMA Galton Watson processes. So let me now go to the setting of branching Markov processes. Okay, before that, just a reminder of what we saw before is that all the criteria, all the results we got, and all the information about these BNMA Galton Watson processes, we know it is coded by branching, what is called the branching mechanism, which is the generating function f, and the immigration mechanism, which is given by the generating function g, that is giving us the size of the typical immigrating family, or the size of the typical families in the system. Okay, so we want to know if in a more general setting, there are similar results that are valid, that are preserved. In particular, when we have movement of particles, branching of particles, immigration of particles, all of that in continuous time. Are there any questions so far? No?
I have a question, Victor. So
Yeah.
in your picture, you have different colors for the individuals. Are we talking about multi-type branching processes, or they're in one dimension?
I mean, in this case, in what I was describing, no, it's just about one type populations. But in the general model, we are going to allow multi-type particles to migrate to be in the system. And actually, that is one of the examples we can consider here, okay, when there are a finite number of types.
Great, thanks.
Other questions? Okay. Well, so I pass to branching Markov processes. So here we have particles that are going to be moving in the space E, okay? That is going to be done according to some semigroup of some Markov process in E, okay? And then with a rate beta that may depend on the space, this beta of x, we are going to have branching events, okay? So here there is a branching event, and we have two possibilities. We have the first possibility where that the new particles take the same position of the mother particle, and then they evolve independently, okay? Or the new particles can take new positions, okay? So we are going to say that the branching is non-local, where the particles take new positions, okay? So that is like introducing jumps. And we are going to say the branching is local if the new particles are taking the particle of the mother cell. Okay. So when we have a branching event. These new particles are going to take some positions that we are going to denote by x1 up to x capital N of x. Capital N of x is the number of particles that are coming into the system, and I will be assuming that N of x is finite with probability 1. Okay, so we can just understand this by saying that there is a random atomic measure that is introduced into the system. Okay, so we describe that random atomic measure by a measure chi that is given by the positions of the incoming particles. And well, this is just a sum up of what I said before. So we are going to need the semigroup of the typical movement of the particle, the rate of branching. By this rate of the particle, we mean that if we condition on the path of the particle, then the probability that the particle has not branched by time t is going to be exponential of the integral between 0 and t of beta Zs ds. Okay, so we introduce this new cloud of particles that is given by the measure chi. And this is important to say that the law of this cloud of particles is going to depend on where the mother particle was when this branching event occur. Okay, so we are going to denote the law of this cloud of particles by calligraphic E of little x for the position and chi for the measure. Okay, so this model has now a branching mechanism that is telling us what is happening instantaneously. Okay, so instantaneously with a rate beta, there is a branching event, and we pass from a single particle at position x into a cloud of particles that are going to be described by this product of g of xg that is describing the new positions of the particles. In the case where all the particles have the same position as the mother particle, then the case of local branching, where all the branching is local, we have that this branching mechanism is actually given by the generating function of the number of particles that appear evaluated as g of x. Okay, and we will be assuming that these are true branching events. So the probability of having only one particle appearing in a branching event is going to be 0. Okay, so if we let the particles evolve for t unities of time, we are going to have a random number of particles that we are going to denote by capital N t. Those particles are going to be located at positions x1 t, x capital N t of t. Okay, so we can actually describe the population by an atomic measure that is evolving with time t. Okay, so at time t, we have another random atomic measure that is given by the Dirac masses of the positions of the particle at time t. And we are going to have that this cloud of particles is going to be Markovian in the space of atomic measures in the space E. Okay. Well, I described what happens when we start with a single particle, but again, because all the particles behave independently, all the movements and branching is assumed to be independent, starting from n particles is just like adding n independent populations. Okay, so the law starting from a cloud of particles given by mu is just the product measure of starting with the individual populations that are described by a Dirac mass at position yi. Okay. With this description, we are going to be saying that we are working with a spatial branching process that is a branching Markov process. It is determined by the semigroup PT and the branching mechanism G. Okay. Well, for studying this process, so I haven't spoken yet about immigration, but still without immigration, we need to study, as in the previous case, the generating function. Okay, the generating function now is varying in continuous time, and we are going to take the generating function by the expected value of this bracket g xt, and g of a measure mu is given by the product of g of the position evaluated at the positions of the particles that define the atomic measure mu. Okay, so this g of xt is g of the positions of the particles at time t. Okay, because we have some movement and we have branching with a rate beta, we are going to have that this generating function vt is going to satisfy an evolution equation that has two terms, the transport of the particles and the branching. Okay, so if we look at what has happened at time t, we have two possibilities: no branching or branching. If there is no branching and we started with a particle at position x, we are just going to see where this particle has moved in t units of time. That has happened according to the semigroup PT. Okay, and it can be the case that at time t there has been already a branching event at some time s. Okay, so we are going to see where that particle move. That is going to be described by this term ps, and from there we're going to let evolve the particles for the remaining time. So this is what is being said here. Okay, so there is a branching event at time s for the particle move as units of time, and from that position we have branching, and we let the new particles to evolve for the remaining time t minus s. Okay, so some examples, couple of examples. We can think, for instance, of branching Brownian motion, okay, that is living in a bounded domain, this domain D, E here, okay, and we can assume that the boundary is Lipschitz absorbing boundary, absorbing Lipschitz boundary, okay, and we can think that the particles are moving as a Brownian motion, and they are going to be killed at the first hitting time of the boundary, and they are going to branch with a constant rate. Okay, so the rate is going to be constant for all the particles for all the positions, and once there is a branching, the new particles are going to behave again as a Brownian motion killed at the first hitting time of the boundary. Okay, so it is important to say here that in this case we are losing mass by two events, by either killing or by having branchings that are not successful, that are not giving new particles. Okay, well, in this case, the branching mechanism is given by the constant rate and just the generating function f of the number of particles that are being beget at each branching event, like in here. Okay. There is another model that is being studied, in particular by Andreas Cipriano, for nuclear reactors. We have neutron branching processes. In this case, the particles are living in R3 times v, and v is the set of velocities of the particles. That those velocities in reactors is known to have is to be bounded below by a v mean that is strictly positive, by above by a v max that is the maximum velocity that the neutron can take, okay? And they are gonna move linearly and change direction, move linearly, change direction, and so on. And they are gonna be killed when they hit, again, the walls of the reactor, okay? And there is gonna be a branching event that is given by a rate that is called the cross section that depends on the position of the particle and the velocity of the particle, okay? And in this case, when there is a fission event, a branching event, the neutrons are going to give birth to new neutrons. The neutrons are going to have the same position as the original neutron, okay? But they are going to have different velocities, okay? So the branching is not is non-local, okay? So the position is being preserved, but the velocities is being changed. So this is going to give us that the branching mechanism is given by this rate, and then the expected value of this product of the number of created neutrons and given by the new velocities of the neutrons. Another example that I didn't describe here, but that Adrian was wondering, is the case where we have new particles arriving that are taking new types or that are bringing new types to the population. Okay. Now I'm gonna describe what happens when we have immigration. So as before, we have particles evolving and branching, and at some moment there are new particles coming. Okay, those new particles are going to be described by a new atomic measure. Okay, and once these new particles are into the system, they are just going to behave independently of the other particles and imitating the behavior. So they are going to move according to the same Markov process in E, okay? And they are going to branch in the same manner as these particles that were present in the system, okay? These branching events, we are going to assume that they appear in time according to a homogeneous Poisson process with constant rate gamma, okay? And the law is going to be described by some law pi t, okay? Okay, so when there is an immigration event, a new random atomic measure is going to appear as before. That is going to be independent of the states where the particles are. Okay, so there is no dependence here of the position of the particles. Okay, and this is going to make an immigration mechanism that we are going to write by h of g, that is given by the rate of branching, the rate of immigration, sorry, and this calligraphic EY that is telling us how or where the particles are landing. Okay. So if we look at the position of the particles at time t, or where or how many particles we have at time t, we are going to have the contribution of the original cloud of particles and the immigrating populations. Okay, so the immigrating populations are going to appear at times tau I, and they are going to start with a new cloud of particles y I. Okay, and these y are going to be independent of these terms here. Okay, so this tau I are the arrival times of a Poisson process pi t, and this xt is just the original branching Markov process characterized by the semigroup P and the branching mechanism G. Okay, and when we start with a cloud of particles P mu, we are going to denote the law by P mu as before. Okay, So this is, again, a repetition of what I said before. So the population at time t is, so if we see what happens at time t, we have what has brought the original population, and then has brought the incoming populations. Okay, they appear at times tau 1, tau 2, and then we let them evolve for the remaining times. Okay, so we have to study the law of this population at time t. Again, this process is going to be Markovian in continuous time in this state space of atomic measures in E. Okay, and it's going to be described by the generating function, which is a nonlinear semigroup VWT, which is given by the generating function of yt in a function g. As before, it is given by the product of g of y t I, as in here. And this generating function is going to satisfy another evolution equation that can be summarized by this expression. So we have that Wt is given by Vt, that is telling us the contribution of the original population, and then this term that is just describing what is happening with the immigrants that are arriving in sometime s in the interval 0t. This formula is actually just obtained by Campbell's formula for using this description. Okay. So now that we have this expression, then we can study the asymptotic behavior of the size of the population, essentially by taking limits here and determining when this is having a limit. Okay, but to say what is happening in here, we have to say what is happening in this semigroup in large times. Okay, so we need some assumptions for that. That is what I'm going to describe now. Okay, the assumptions are similar to the ones I described before for the minimum Galton Watson process. So we will be assuming that the size of the typical families in the population has a finite variance that is uniformly finite, and that we are going to write that condition in this form. So the supremum, independently on where the population is branching, has a second moment that is finite. Okay, and then we are going to be considering also the expectation or mean semigroup, which is just telling us the size of the expected value of the size of the population at time t. Okay, so it's expected value of this bracket f of xt. F comma xt is just this typical integral f with respect to the mu, with the measure mu. The measure mu is being replaced by xt. So it determines the average size of the population at time t. Okay, and we will be assuming something on the behavior of this semigroup. We will be assuming that it satisfies a Perron-Frobenious type behavior. For that, we will be assuming that there is an eigenvalue lambda, an eigenfunction phi, and an eigenmeasure bar phi tilde. Okay, such that when we start, or when we average this semigroup TT with respect to the eigenmeasure phi tilde, what we get is an exponential of f integrating phi tilde. Okay, and then if we evaluate the semigroup at the eigenfunction bar phi, what we get is exponential of minus lambda t times the eigenfunction, and we are going to integrate with any measure mu. And furthermore, we are going to assume that the asymptotic behavior is also determined by this. So we are going to be assuming that the asymptotic behavior of the semigroup is exponential and described by the eigenfunction, eigenmeasure, and there is an error term, and this error is actually going to zero exponentially fast. uniformly in the space and the functions we are considering. Okay, so this is just a condition of the type spectral gap of the semigroup. It looks like a very constraining condition, but actually it's not that constraining. We can show the examples I described before satisfy this condition by using actually that the movement of the particle has satisfies a similar condition through the semigroup. Okay, so if the semigroup describing the position of the particle is satisfying a similar description, and we can we can control the branching rate and the branching mechanism, then we can prove that the mean semigroup is also satisfying such a condition. Okay, so this is also a kind of quasi-stationary behavior for the semigroup PT. Are there questions or comments? Okay. Well, so the typical mean, the mean of the population, when we have this condition being satisfied, we have that it's gonna decrease exponentially fast if lambda is strictly positive. That is just saying that the population is going to zero. That is the case subcritical. The population is going to remain stable if lambda is equal to zero, and it's going to grow exponentially fast if lambda is smaller than zero. That is the case of a supercritical population, and we will not be looking at the supercritical case. But this is the typical behavior we will expect of a population of this kind. Okay, so we will be assuming that the typical family is getting extinct in a finite time. It's important to make this assumption because as we have a movement of particles and the space can be as large as we want, we can have that the population is just going to zero in the subcritical case, but not actually to becoming zero. So we are going to be assuming that the population is really zero at some moment, and we are going to assume this covariance type condition, just telling that the covariance of the position of two particles is strictly positive in when we are averaging with respect to the quasi-stationary or with respect to the eigenmeasure bar phi tilde. This condition is also not very restrictive. It can be verified when, for instance, there is some local branching. Okay, under all this assumption, we can finally write our result when there is no immigration. Okay, so when there is no immigration and we have a critical population size lambda equal 0, we have that there is a Kolmogorov limit as before. We have that the time of extinction of the population is decreasing linearly with t. Okay, and the limit is given by, as I said before, the covariance of the two particles evaluated in the eigenfunction is an average with the eigenmeasure. Okay, and this term that is describing where the particles are being positioned, where we are starting with a typical particle mu. Sorry, not with a typical particle, with a cloud of particles mu. Okay, this v of mu is just the covariance of the two particles in a typical regime or in the stationary regime. And that term is going to also characterize the Yaglom limit. So we, under the conditions I described, conditions 1 to 4, we have that there is also a Yaglom limit when we condition on the population not being extinct at time t. Okay, so we have that the size of the population is going to infinity with t in a linear way. Okay, so that when we take this conditional law, what we get is an exponential random variable. So this conditionally on the population not being extinct, this random variable is going to another random variable that is exponential, and the parameters of this exponential are totally described by this term that is given in terms of the branching rate, okay? And this other term that is telling us where the particles are being located in the typical case, in the stationary case, as t goes to infinity. So according to this, to the quasi-stationary distribution, Barphi tilde. Okay, when we add branching, we know from the discrete setting, we should have a similar behavior. So we don't need to condition anymore, but we have that the population size in the critical case when the immigration has a finite size, okay? That is, the size of the family is growing linearly, and in the limit, what we have is a gamma random variable with parameters that are determined as before by the branching rate, and this term that is given as before by the quotient of the immigration and the variance of the particles, well, the covariance in this case of the particles. So in the discrete case, we have this term that described the gamma limit random variable. Okay, what happens now in the subcritical case? Well, we are going to have a limit if there is a log moment condition that is being satisfied. So we already said what happens in the critical case. So the remaining case is what happens in the subcritical case. In the subcritical case, when we have these two assumptions, so the mean semigroup having an eigenfunction and an eigenmeasure and so on, with a rate lambda, so that is subcritical, we have that there is a measure y infinity, and that measure y infinity is going to be the weak limit of the population cloud yt as t goes to infinity, and this will happen if and only if this integral test is satisfied. As before, it's an integral test only in the immigration mechanism, and this can be also formulated in a log moment condition. Okay, there is a log moment condition with respect to what is happening under the eigenfunction Barphi. That is somehow describing what is happening typically in the stationary regime or quasi-stationary regime. Okay, well, the proof of this, I'm not gonna give the details, but it's again this studying when this kind of integral is finite, and that it needs the description of the typical behavior of this semigroup. And for that, we need the conditions on the existence of the eigenfunction and eigenmeasure. Okay. Well, what happens in the more general setting of superprocesses? The same results that I described before are true. Okay, exactly the same results. So we just need to introduce a bit more of tools to work with that. So we need to describe the local branching mechanism. That is when we create or we introduce new masses of particles according to the positions where we are. Okay, so the branching mechanism is going to be given by the Laplace exponent of some spectrally positive Levy process whose characteristics depend on the position where we are looking at a particle. Okay, and then there is the non-local branching mechanism that can be expressed by the rate beta of x, and then this f of x minus eta of x f, and this eta xf can be written by this kind of linear term that is like a drift, like a continuous creation of mass, of appearance of mass, and then this other term that is like a jump event. All this looks like the Laplace exponent of a subordinator of a Levy process with non-decreasing paths. And this non-local branching mechanism will be satisfying these conditions, and these models, these superprocesses, these superprocesses were studied by Dawson, Gorostiza, and Lee in 2002. Sorry. To study these superprocesses with immigration, we need what is called the Dinkin measure or excursion measure of the branching population, which is telling us how the population is typically evolving, okay? And then the immigration mechanism that I described, no, I didn't describe, I described the non-local, but there is also the immigration mechanism. This immigration mechanism is similar to the non-local branching mechanism, but there is no dependence on the positions where we are. And well, we can also describe this branching mechanism by saying, well, we are going to migrate a finite measure that describes the cloud of a population, okay? And that cloud of population is going to be finite, okay? So we can think of that as giving a size, and then that we fix the size according to this kernel. We are introducing the population is just a probability measure, okay? And the total mass is the probability measure times u. So the total mass is u. Okay, because we have immigration, what has happened at time t is described by what happens at the population at time t, and what happens at the immigration. Immigration is described according to a Poisson random measure. In time, we have constant rate, and in space, we have the immigration mechanism that is giving us, that is describing everything. Using that and Campbell's formula, we can just get the Laplace transform of the size of the population that is that can be expressed by this formula. And again, this term is giving us what is happening in the original population, and this other term is giving us what happens with the immigration events. And well, that's it about all the setting. So all the conditions we expressed before for the branching Markov process have a translation in terms of this branching and immigration mechanism. And under those conditions, we have a similar result as before. I'm not gonna state the precise result, but it's the same as we saw before. Well, all the details of this is in the preprint that is in archive. You can have a look if you're interested about more information on that. And as I said before, there is another preprint by Andreas, Pedro, and Natalia that studied the case where the variance is. And this being said, I thank you for your attention, or obrigado pela sua atenção. Thank you very much.
Thanks a lot, Victor.
Questions? Yeah.
Are there questions? Yeah, Andres.
Thank you. Hi, Victor.
Hola.
Just a really hola. Just a really quick question. When you're working in the super process case, the techniques that you use involve like the backbone to translate things from the branching Markov process to the super process.
We did not really use, I mean, we didn't use many properties of the backbone, but actually in the other paper of Natalia, Andreas, and Pedro, they are exploiting more the spine or the backbone.
And also really quick, what happens in the, I know it's another paper, but what's the difference when you have like infinite variance? For instance, you have like
when there is
stable.
infinite, you have similar results, just all the terms I mean, in this case, when you have infinite variance, then you will not be normalizing by tip, you will be normalizing by a regularly varying function, okay? As in here, you're gonna be normalizing by a regularly varying function, but the rest is just the same. They didn't look at the immigration case yet. They just look at the Yaglom and the Kolmogorov case.
But the non-local branching, they studied too.
Yeah, they studied non-local branching. Yeah, just this. So what they changed is this finite variance assumption. They're assuming that there is a finite mean and some regularly varying of order between 1 and 2.
And can you play in the variances with the local and the non-local? To assume, for instance, that the local has infinite variance and the non-local, some interplay between those and obtain different things.
I don't know if they have done that, but it is formulated jointly, okay? So with the two terms, so you can split it and see who is ruling indeed.
Yeah, exactly.
But yeah.
Thank you.
Thank you.
In the meantime, I'm Dario. Hi, I've been
Hola,
promoted
Dario.
as moderator because Adrian had to run just 1 second ago. So first of all, he said to thank you and thank all the attendants. And I join Adrian in thanking everyone, especially the speaker. Is there any other question before we leave?
Yeah, actually, I had one. Concerning the supercritical phase, I know it's not part of the work, but is there any way to know if the number of particles is behaving like the expectation? Like it's growing?
Yeah, like this term. Yeah, like this exponential lambda t here.
Yeah, we know that in expectation it's growing the supercritical phase, but maybe there's no particle left.
Exactly. Yeah, I mean, it will depend on this measure also. I think there should be some work about that. I don't remember at the moment what is happening in this supercritical case, but I will look to the paper of not to the paper, to the book of Lee, where he has actually some results about this. So the result actually I show in the immigration setting, there was a particular version of it that was known and that can be read in the book by Lee. So I will look for that supercritical case in the book by Lee. Sorry, I cannot answer precisely.
Oh, great. Thank you. I'll take a look at the book too. If you can share it with me, please.
Yeah, definitely. Yeah, I can find could you drop me an
it can be
email?
later,
I can. Yeah, if you can drop me an email, I will.
I'll contact you.
Yeah.
Thank you.
Thank you. I have a question, just given that we are anyway over time. Is there anything that we can know about how far from being reversible this process, the non-local processes are? Let's say
You mean backwards, looking backwards at
yes,
the process?
Yeah. So, well, my background is that if you take a Dawson Watanabe superprocess with linear immigration, independent immigration, you get reversibility, and that's a fact. So if you complicate things in a non-local setting, maybe you still keep linear immigration. I would say I would be surprised that there are many such processes that are reversible, but maybe you can study how far from it being reversible, if there is any sort of distance. And I guess that all the tools that you have, some insight a priori. It's easy to guess, no? But then, do you know anything about it?
No, I don't know anything about that. Actually, Emmanuel was asking the other day about also the genealogy of these processes and so, but I don't know about it. I mean, we have to see what it is happening, but I guess again it's gonna be determined, or a lot of it should be coming from what is happening in the quasi-stationary regime, and where the particles are not extinct.
Thanks. Thank you.
Thank you, Dario.
If there is no other question, I think let's thank again Victor in any way possible.
Thank you.
Yeah, I don't know what's going to be the next talk, because I'm normally not part of this, being in a different part of the world, but hope to see you all again, and let's get on with the day. Thanks a lot.
Gracias, Víctor. Pablo aquí.
Gracias,
Muy
Pablo.
buenas.
Gracias a todos.
Bye.
Gusto en verlos.
Gracias,
Good to
Adrián.
see
Nos
you.
vemos.
Thank you for inviting me. It was very nice to be here or there.
Thank you.